learning to play Minecraft with video pre-training. That's not only this idea of how to collect a lot of data and label this data, but it's also about the architecture itself, because after the collection of these 70,000 hours of video, the next step is to train a behavioral cloning architecture to pre-train a latent space that is useful for Minecraft any task. Let's take a look. What do they want to achieve? So what is a benchmark that they want to solve? Because, well, in Minecraft you can do anything, and therefore it's hard to measure whether the agent performs well or not well. Therefore, we need some specific task to measure the performance in a form of some value. And in this particular case, this benchmark was find a diamond, because in order to find a diamond, there is a sequence of crafting events that has to happen. So first, the agent has to collect a wooden log, then to craft a wooden plank and a crafting table, and out of the crafting table to create a wooden pickaxe that can be used to collect cobblestone. And when we have this material, we can create stone pickaxe. It's just some part of the tree. And with stone pickaxe, it's possible to get iron ore. Then we can craft furnace, and out of that make an iron pickaxe. And only then, with iron pickaxe, it's possible to collect diamond. So that's not possible to collect that without iron pickaxe. And after that, it's even possible to create a diamond pickaxe. So there is a long-term goal which has to be achieved. And another peculiarity of the process is that this part has to be done above the surface of the ground to collect a wooden log. The agent has to collect enough wooden log because it's also being used late in the process. After that, the agent has to dig down a hole in the ground, and basically it's barely possible to get upstairs after that. So the agent has to commit to go under the ground. Yeah, so this is a long-term goal, and this particular architecture was able to learn to achieve this goal. And the way to do that, they use a behavioral cloning. They ask human players to play the game, collect a diamond, and they recorded actions, recorded videos, 2,000 hours of collected videos from humans. And this information was enough to train a behavioral cloning approach, like to fine-tune the pre-trained architecture. And now the architecture can achieve this goal to find a diamond itself. So that's the benchmark. The complexity of this task is a long-term goal that's usually quite complicated for reinforcement learning. Therefore, pure reinforcement learning, where the agent has to explore environment, that's barely possible to achieve this long-term goal to find a diamond just by using exploration, because out of random exploration there is infinite amount of opportunities what can happen. The computational demand is too high just to solve it via pure reinforcement learning with exploration, with self-exploration. Even though there were some approaches to solve that with pure reinforcement learning, and for that the reward was also progressive. So for example, 1 reward to obtain wooden plank, 2 for crafting a table, 4 for crafting wooden pickaxe, 8, 16, 32, 64. For every next level of this long-term goal, the reward was much higher. But even with such structure of the reward, the task is not feasible with pure reinforcement learning and exploration. But behavioral cloning, or combination of behavioral cloning and reinforcement learning, is a solution for this long-term problem. One problem of these long-term tasks is that the agent has to know its current state, because let's say when the agent is under the ground, it has to realize that it already achieved everything in the past, what it has, whether these resources enough to go underground, not to lose all resources. For example, the agent can just create many crafting tables when they are not necessary. Therefore, if the agent already made a crafting table, it has to keep that in memory, that okay, this is over. Now I need to craft something, crafting table. So this is all motivation of the architecture that I'm going to describe next. Well, basically we need memory. Previously, recurrent neural networks were some type of architecture which contains some temporal memory. And in this architecture, in video pre-training architecture, which you can find if you follow here view code and model weights, they are based on transformers. Here, this is our work, but this VPT architecture is what we borrowed from here. The architecture is the following. First, we take an image of the current view, which is 128 times 128 spatial resolution times 3 channels, RGB. So this is a 3D matrix that goes into just encoder CNN. This encoder CNN is this Impala CNN. So this is just a name of CNN which has a paper and some specific type of architecture, but it's just a normal convolutional neural network. It takes as an input this 3D matrix and outputs a vector. This is embedded vector. Basically, this spatial resolution is being translated into just 1 pixel with 1024 channels. So out of these 3 channels, after many layers of this CNN, we get 1024 channels, 1 pixel for the spatial resolution. So that means that we know activation of 1024 features which represent the environment, but we don't really have a very good spatial understanding. It's more like a bag of words, bag of features that describe the current image. So this representation we feed into a transformer which has 4 blocks. So 4 blocks means these are 4 sequential blocks. It's the same as with multi-layer perceptron. We can have 4 sequential layers, and here we have 4 sequential transformer blocks. So what is a transformer? Let me try to explain that in a short form. So as an input, we have vectors. Let's take, for example, 4 vectors. And let's imagine that each of these vector has 1024 values. Then we have Q, key, and value streams. That means that this Q, key, and values, this is usually just multi-layer perceptron layer, just a single one usually. And they have independent weights. So these are independent multi-layer perceptrons. And then you take this embedding and pass through this multiple layer perceptron layer. You can do the same for keys. And so you take the same vector and the same vector, you pass through the value. And at the end, you have 3 vectors for Q, key, and value. Then we do the same for another embedded vector, and so on. So here, this will be time step t plus 1. This is time step t plus 3. So remember, we get that after we feed the image through a convolutional neural network, and we get this embedding. So these are our embeddings that we have here. Temporal information is represented by these embeddings, and then we feed these embeddings through Q, key, value and get representations for Q, key, and value. What we do next is, if we simplify the process, we have this like a matrix. We take a dot product of this pair, and then dot product of this pair, and of this pair, and so on. And then we get the coefficients, and these coefficients help to decide in what proportion to mix between each other these vectors from the value stream. You can think about a transformer as a multi-layer perceptron, but the weights of this multi-layer perceptron are computed on the fly. Here, you first compute weights of the multi-layer perceptron, and after that, you compute the processing step of the value stream. So something like pre-computes the weights of the network on the fly based on the input information, and then process this information. So this is a short story about transformer. And what we have in this transformer, we have 128 time steps in the memory. So for every time step, we encode it in CNN. And this encoding we process via queue, key, and value pre-processing layers. And actually, these two outputs we store in memory. So here in memory, we store the key and value embeddings for the past 128 time steps. And whenever we have already more than 128 time steps, we pop the most oldest pair in the memory. Here we have 128 time steps from the memory and plus one, which is the current, like embedding that represents the current image. And what is important is this, that we have keep in memory only key and values, but the queue, so what we have after the multilayer perceptron queue, we broadcast it to all pairs of key and value in the memory. So because in order to do a processing in a transformer, we need all three components. So this key and value we take from memory, which is saved from the time step when the encoding was the current one, and the queue stream we take from the current image. So we'll do the processing here, and these embeddings in this case only red one, because red one here is the current. In this case, what happens is that we take the current time step, we encode that through the queue multilayer perceptron, and we broadcast that at all time steps, at time step t, t-1, t-3. Why do we need that, or why is it helpful? That's helpful because in key and value, we can encode something related to the time step, contextual information, and the queue information can come from the current time step. So basically, there's always a connection between current time step and the past history, because we broadcast our current queue embedding to all time steps in the memory. And therefore, the next steps of the transformer processing of this value stream always conditioned on the complete history that we have in the memory replay, and also conditioned on the current situation, which is encoded as a broadcasting of Q value of the current image. Then we repeat this procedure 4 times because we have 4 transformer blocks. Also, these are residual connections. That means that we take our vector 1024 and the result of the first transformer block, this is our vector. Then we process that with transformer. So because we use memory, we have 129 outputs. So 129. So this is 1 plus 128 in the memory. So this one represents the current time step. And then we have like addition procedure. So this one plus this one. And out of that, we have the embeddings. The results of the computation of transformer just change with addition the input encoding. So we repeat that 4 times, and at the end, after 4 blocks, so there is a last transformer block. It provides us 129 outputs. One is from the current image stream and the other 128 from memory stream. And we take this current image stream embedding, and out of that we have 2 heads. There are multilayer perceptrons. And then after this multilayer perceptron, we have a label output of size 8641. This represents a combination of keyboard actions that the human players can do and that the agent can do. So that's a combination. So for example, if the agent moves forward, that would be one action. This would be one hot encoded vector, which represents the action move forward. But if we press 2 keys simultaneously, let's say move forward and turn left, then it will be a different one hot encoded vector, a vector that represents move forward. And that will be a vector that represents move forward and left. And this would be a vector that represents move forward and right, for example. So by combining just a little number of actions that human players can execute on a keyboard, just due to the fact that they are combinatorial, we have such a large number of 8,641. So this is what the agent is trying to predict. One hot encoded label of the action that is provided by the demonstration. And it has some output, which then can be used either as a softmax. So because the output of the neural network will be most probably usually something like 0.9 and so on. And then it's possible to just select the highest one. That would be a greedy approach. A different approach is a probabilistic prediction. So we can apply first softmax to make it sum up to 1. And then we have a probabilistic approach that with 90% this action will be executed, with 10% this action will be executed, and with 0% chance this action will be executed, like this action, and this one hot encoded action. So what you can do, you can make a threshold and make a random generator that generates a continuous value between 0 and 1. And if the random value is, for example, 0.55, then it's here, and that will be our 90% action. And if the random value is, let's say, 0.95, then this will result in this 10% action. That would be a probabilistic prediction. But at the end, we have a loss function because we have the current image input, we have memory, and we have the label because this is a behavioral cloning. So we have, that would be our X, and that would be our Y. And we have model fit XY. So this is one head. And the second head is about computer mouse movements. We can encode computer mouse movements also as one hot encoded with 121 possible values. We can take, for example, a mouse movement 0, that would be here. Computer mouse doesn't move. And then we can make a grid out of all possible mouse movements. This grid represents the delta, so delta x and delta y. So we take time step t and time step t minus 1. Computer mouse was moved to this delta x and delta y. This computer mouse movement in per one time step lands here, and this will be our one hot encoded value, 1 here and 0 everywhere else. And because this is now 11 times 11 grid, 5 steps left, 5 steps right, 5 steps up, and 5 steps down, and also our 0. So it's 11 times 11. We can flatten this 2D representation into one-dimensional vector with 121 values. And that's how we have one hot encoded representation of computer mouse. So it doesn't need to be necessarily Euclidean displacements. If we compute all deltas per time step, we can have a bit dense grid in the middle and then more sparser grid cells at the outskirts. Another thing what is possible to do is to apply, for example, k-means on this distribution and just measure cluster centers of 121 clusters. And then this one hot encoding will represent the nearest cluster center of the current mouse movement. So there are possible alternatives how exactly to assign a current mouse movement to what ID of activation, because in this representation there is no information about the proximity. Activation of this doesn't necessarily mean that activation of adjacent vector value has some similarities. So they can represent completely different values of mouse movement. So therefore, these are just very independent values. And the same is relevant here. So if we have a vector with 8,000 values and activation of this value has nothing to do in terms of similarity with activation of this value. So this one can be move forward and this one can be jump This is very independent. After training is over, we need to evaluate agent, for example, how good it can obtain diamond. And then the network is making a prediction, and we can select a probabilistic action based on the activations of every value in the vector. And for training, the value that is actually executed in the data set should have the highest value in this output. It has to get closer to 1. Positive example is 1 and not activated example is 0. And the rest, and this loss function push the rest of activations towards 0, and the correct activation, it pushes toward 1. Okay, so we have now a basic understanding, just from meta perspective, how that all works. Now, if we come back to the original paper, they say here that they do pre-training of VPT foundation model with 70,000 hours of video labeled with mouse and keyboard actions. This architecture is being pre-trained on 70,000 hours of videos with labeled keyboard and mouse actions. And now we have this latent representation. We do training of multilayer perceptron, we do training of the transformer blocks. Let's assume we also train CNN, so everything is trained. When this training is over, now we have very good latent representation. This is latent space. This is useful for any other task of playing Minecraft because it was trained on many different tasks. And now we just have this latent representation, which is 1024 dimensional, where point has certain meaning. So this point has a meaning based on the current situation as well as some memory from the past. And now we can fine-tune based on this representation, because the training of based on 70,000 hours of the complete architecture is computationally heavy, not feasible on a local machine. But what is possible to do is train this latent space and then use that, like freeze here everything. So freeze the weights of the encoder, of the transformer blocks, and then just do a training, get diamond task. It can be reinforcement learning or behavioral cloning. We just can further train only these multi-layer perceptron heads. And moreover, we can train that only on the task demonstrations. We can collect like 10 minutes, maybe let's say one hour of human playing a particular game and solving a task. It can be hunting animal. So for example, there is a human player that just doing hunting animal, and we can collect information about visual input and the actions that the human player executed. And based only on this small amount of information, maybe 10 minutes, maybe 1 hour, it's possible to fine-tune this architecture, and the agent can perform this task pretty well. This fine-tuning can happen, for example, only for these multilayer perceptrons, but also it can happen for the complete architecture. It will be a bit more computationally heavy, but still it's possible to let gradients update also weights of the transformer blocks and encoder CNN. So this is already hyperparameters tuning, but it's also possible just to update the weights of these multi-layer perceptrons. So let's quickly go through the pseudocode. So there is Q, key, and value. There is current embedding. We feed it through the transformer blocks, and we append memory keys with the current key, and we append a memory value with current value, and then we compute transformer block. Here we repeat the query of the current embedding 129 times and broadcast that to the rest of the embeddings. We take the stack of keys from the memory, the stack of values from the memory, 129 values, and then do transformer block computation, and then delete the oldest entering memory and value stacks. And then use for the next block only current frame embedding, and then continue to the next block. So let's also quickly discuss our solution in this. So here they have a competition. So our team took second place in this competition and also was awarded with 2 prizes. So you can find more details in this paper if you search on Google Scholar. So what we did here to make the agent perform different tasks, like find a cave, make a waterfall, catch a pet, build a house. We let the agent start to do something in the environment, and then we have like embedding representation of the current state of the agent in the environment. This is a vector of size 1024. And that's our current point in latent space that represents our current situation of the agent. Then we created millions of points in the same space in the demonstration dataset, because for every task, for example, find a cave, we have demonstrations where the human player is performing the task. For example, find a cave. So here is a cave, that's the cave. And when the human player finds a cave, it presses the button, I found the cave, and the episode ends. So here everywhere there is some exploration of terrain until some entrance to the cave is found, and then the agent goes inside the cave, or human player goes inside the cave. And this is a demonstration data set. And for every time step, it is possible to create an embedding in latent space. Which also, of course, takes into account the previous time steps. So let's say if we have 1000 steps per episode, and if we have 100 episodes, then we have 100,000 points in this latent space. And when we have this 100,000 points in latent space, then we can do a similarity search. We can find what are the nearest points to our current point. So we have our current point, which changes every time step because agent interacts with the environment, and this interaction updates this current frame embedding, and therefore the point that represents the current step changes. But still, it's possible to find the nearest point from the dataset, because the 100,000 points from the dataset, they are static. So our current point is constantly moving with every time step, and all points from the dataset, they are static. Then when we find the nearest point in this latent space, or set of candidates of the nearest points, we can just proceed with copy actions from human players. Here is an example. So a similarity search and divergence of 5 pairs of simulate and dataset station trajectories. So left column, current frame form from the MyNRL environment, and this column is the current reference frame from the dataset trajectory that the agent follows. When we find the nearest point in the dataset, we can visualize, because we know the ID of the trajectory and we know the ID of the time step, and so we can visualize what the agent actually see at this time step in the dataset. So here is what the agent see in the dataset, and here what our agent see in the environment when it's interacting with the environment. And other examples and other examples. So of course there could be some similarity in latent space, but not in reality. For example, here you can see this is a mountain far away, and here you can see there is even some lake dozens of meters away. And here, although it looks similar, but this is a stair in the vicinity of the agent. So in latent space, these two situations look quite similar, but in reality, they are not. It has a room for improvement. Or for example, here, let's see what the agent see. So it has to climb up, but in the dataset, the nearest point represents also stairs, but here the agent has to go down. But anyway, if we find this similarity, we say, okay, this is our trajectory, which is the most similar to what our agent is perceiving right now. And then we just start to copy trajectories from this situation, because there's human player, which just executes keyboard commands and mouse commands, and we can just copy them and let our agent to execute the same commands. Or alternatively, we can find like some candidates, because this is just the nearest point, but we can find not just a single one, but candidates, and do some interpolation between them. Further fine-tuning is possible, but I'm just trying to convey the general idea. And here on the right side, you see the similarity measure. So the current time step is represented by this bold dot. For every example, it's at the end. So by blue and red, we here represent a next similarity search. So because let's say we found here that this is very similar situations, and we just want to follow the trajectory, but of course we don't want to switch between trajectories every time step, because then that would be probably pretty random sequence of actions. We just want to follow a given sequence of actions because we assume that two situations are similar, and we want to follow them for like several seconds. So here we have 256 time steps from left to right, frames per second like 20. So for example, these colored lines represent a new search. So sometimes it happens more often, like in this case, where the station is maybe not so similar. And here it happens less often. So that means that here for about 100 steps, we just follow the actions by copy pasting the actions from this agent and copy pasting them to our agent. And then there are two events possible. One event, we just do a next similarity search. This is the event of a new similarity search, just to avoid stations when it's stuck somewhere and similarity is good, but it's still stuck, let's say in front of a stair and can't move any further. We just do anyway a new search, and then the new trajectory is found and the agent follows this new trajectory by copy pasting actions. And then the red indicates some threshold. So we have some similarity threshold. This is the y-axis represents the difference between embeddings. So it's basically a distance. It's L1 distance between two embedding points. One is our current station of the agent, and second is station point of the dataset. And this is the y-axis represents the difference. And sometimes you see that the current point diverges from the point from the dataset. But this is also like not the same point, because when we start to copy actions, we made a search at this time step, and then what we do is the next time step, we already take a next point in the dataset, because in the dataset this is also as a sequence of points. So this is a sequence of points, and at next time step we take next action from this trajectory and next point, and also next action and next point. So like the trajectory itself, the points from the trajectory itself change with every time step, and the point of the current station of the agent also changes at every time step. Naturally, they can diverge in latent space, and whenever the is higher than some fine-tuned threshold, in this case like 0.35 in L1 matrix, we execute a new search. That means that we find a new trajectory and start to follow that new trajectory either until this threshold is reached again, or until we follow the trajectory for 128 time steps. That resulted in some human-like behavior of the agent. This idea has advantages in comparison to, let's say, reinforcement learning or behavioral cloning, because for both cases there is necessity to train the policy. But what in the method that we proposed, we just do a search. That means that you kind of can load the behavior to an agent just by providing demonstrations. Immediate transfer of behavior based on the dataset of demonstrations. So all you need to do is just encode everything in latent space and then do similarity search. This similarity search provides the agent with the necessary behavior. And then it's also is very easy to update the behavior. If we want the agent to do some updated behavior, like fine-tuned behavior, all we need to do is just to provide some new examples of demonstrations how to behave in this station. Or if we want the agent to avoid doing certain type of behavior, then we may delete some trajectories, or we can apply weights of different trajectories which we think are better and which of them not good to follow. This gives some other perspective of how to control behavior by just updating the dataset of trajectories. You can find here the description of also other solutions and the competition itself, and also about our solution.